Welcome, chemistry students. So in today's lesson, we're going to look at acid and base properties, or acidic and basic properties of salts. Now, this is going to conclude our discussion on acid and base equilibria. We have looked at equilibrium, we've looked at weak acids and bases, we look at acidic and basic equilibria, we've looked at Ka and Kb values. We know that they can ionize, acids and bases ionize to a certain percentage, and we've practiced calculating what that is and then figuring out pHs. So all of that background stuff and what we're doing today, so what we've done, what we're going to do now, is all preparing us for what is coming up in the next few days. Right? So all of that groundwork hopefully will help us transition smoothly into titrations. Okay. So a bit of review though. So two things here. Water can self-ionize. Right, we know that water can self-ionize. It does so in very, very small concentrations. You know, our Kw value for this is quite small. The other review here is that acids and bases will neutralize. They neutralize and they create water and they produce a salt, which essentially is two ions, a cation and an anion. Okay, more on this in just a bit, but just wanted to review those two things. And this slide is, I want to pay attention to the idea behind what cations can tend to do and anions can tend to do, and not so much this example. Right, so I've written here, this is not actually, this example itself, this reaction does not actually happen. We can talk about that later. What would actually happen here in reality is not this, okay? But the idea behind how cations and anions can react, that's what I want the focus to be. Okay, so cations, positive ions, they can tend to, but not necessarily, they can form acidic solutions. How? Because they can attract the hydroxide of water. Okay, so let's just pick any positive, for example, here. I was going to rewrite what is here. But positive ion here, a cation in the presence of water can pull out hydroxide. Look, it can pull out hydroxide. And assuming this is not going to completely ionize, what we're left with is an acidic ion. We're left with a proton with hydrogen. Right, so because of this tendency for a positive cation to attract hydroxide from water, to pull that out of water, aided by water self-ionization, it can produce a hydrogen ion. So it can act as an acidic solution. It has that potential. Anions can do something similar. Okay, they can tend to form basic solutions because they can attract the opposite ion out, a hydrogen ion from water, right? The hydrogen ion from water, thereby generating the basic ion from the Arrhenius definition, the basic ion hydroxide. Right, so this can tend to happen. This specific reaction does not, but it helps to illustrate what cations can do. Okay, a bit of review here as well. Let's review acid and bases and their conjugates. So HCl here we know to be an acid, not just because I'm telling you it is or that it looks familiar. Actually, there should be an AQ here, but we'll ignore that. HCl and its conjugate, you can see here that it has lost or it has donated this proton. That by definition makes it an acid, according to the Bronsted-Lowry definition of acids and bases. Therefore, water as well will be not an acid. Water here will be a base by that same definition, and that is that bases will accept protons, right? So if you look at its conjugate here, look what's happened to it. It's accepted a proton from H2 to H3, and here we have water behaving like a base, and their conjugates are always just opposites. So this acid has a conjugate base. Right, if it does go backwards, this can accept a proton, therefore behaving like a base. And the opposite here, our base will produce a conjugate acid, right, hydronium. Okay, so conjugate bases of strong acids form salts that do not react with water. More on this in just a bit, but not all anions, okay, or salts, conjugate bases from strong salts, from strong acids, will react with water. So they can be neutral. Okay, similarly, the cation of a strong base, let's say potassium hydroxide, and the cation here is potassium, does not react with water in the way that I showed you in the past. So again, more on these two. Hopefully that wasn't too confusing, but more on these two in just a bit. Okay, and here it is, neutral ions. So not all ions or salts are going to have acidic or basic properties. Okay, here are the ones that are neutral. So if they have come from If they could have come from a strong acid or a base, right? Similar examples we've already seen. HCl is a strong acid, hydrochloric acid, or potassium hydroxide is a strong base, sodium hydroxide as well, of course. So these are strong acids and bases. They do not dissociate to produce ions that are acidic or basic. They're neutral. Okay, so the potassium here, the chloride here, they will float around water, interacting with water insofar as their intermolecular forces, but they will not produce acidic or basic properties. Okay, low charge metals such as alkali and alkaline earth metals, so your group 1, group 2 elements in your periodic table, they will not produce ions. And on the far right side of the periodic tables, halogen anions are also neutral ions, so all of your chlorine, bromine, iodine, all that. Halogen, sorry to mention this, halogen anions and most completely dissociated polyatomic anions. For those that list of polyatomics you had to learn back in grade 10, grade 11, most that are completely dissociated are also neutral anions. So an example, let's say, right, if we think back to, all right, nitrate, -1 charge, I'm not going to write that because I'm going to pair that up with this, sodium nitrate. If that dissociates, look, this is a very pH neutral solution here. Here we have a group 1 element, so that classifies here as a neutral cation, and nitrate, another polyatomic that is completely dissociated, ionized in this case. So this will be neutral as well. Okay, so neutral ions. Right, therefore KCl produces a neutral solution, just another example, right? K, potassium and chloride from either side of the periodic tables, they are going to be neutral. Okay, but the real bread and butter here. Okay, so acidic ions. Some salts produce acidic ions when they're dissolved in water. An example is ammonium chloride. So we're going to do something. We're going to ignore chloride. We know that chloride, being a halogen, right? Chloride is a neutral ion. So we're going to ignore that. But when this dissociates, we're going to look at ammonium, right? Okay, ammonium can act like an acidic ion. And more on this, but first, the general idea. So if a salt contains a cation, that is the conjugate acid of a weak base. The rest is not as important, but and an anion that is not a base, that would be chloride. The salt can form an acidic solution. So let's see. So if a weak base produces a conjugate acid, then that can behave like an acid. But it has to be a weak base. That's the key. Okay, so here's a bit more on that. Okay, let's look at this example. So this is, as we said here, okay, this is our weak base. NH3, we know ammonia to be our weak base. And we've seen this reaction before. So what's happening here, we know that it can actually go back and forth, but ammonia and water, HOH, aqueous, liquid, they can produce, this should be a superscript, but this is the reaction that can occur. So ammonia can become ammonium, NH4. Okay, so what we see is this being, start labeling this, what has happened to ammonia? It has gained a proton, which makes this a base. Water here is an acid, not as important in this example, but yes, base, and this would be a conjugate acid, right? If it goes backwards, we know that it's the plus sign here, that can behave like an acid. So it's our conjugate acid, and this is an acid, this is a conjugate base, and that should make sense. Okay, we're focusing on our conjugate acid here. Okay, so because this conjugate acid came from a weak base, what's happening, what I'm saying now is that in water, NH4 can behave like an acid, HOH. That can create an acid, right? It's lost that, so NH3, right? This is behaving like an acid. There are other ions that form acidic solutions we're not going to focus on too much, but it's important to say. So highly charged metal cations, right? Again, you can see that these are often found in the transition group, but iron, aluminum, for example, they can form acidic solutions. And ions that are formed from the partial ionization, not complete, remember complete are neutral ions. So ions that are formed from the partial ionization of polyprotic acids, these often will still contain, so it's not too difficult to remember how this will behave. So this will form acidic ions as well. Right, so this would have come from our first example here. Sulfuric acid, right, dissociates once, right, and this ion will behave like an acid, right, and another dissociation. Okay, now basic ions. So potassium acetate is a highly soluble salt. Now, when that dissociates, potassium and ethanoate ions are produced. Now, potassium is on the far left-hand side of the periodic table. We know it's a neutral ion, so we're going to ignore that. But what is left is your ethanoate ion. Okay, this solution is basic. This solution is basic. And that one of those first slides, I asked you to pay attention to the idea of what happens with anions. Here's where that should hopefully help. Look, this can behave like a base. Okay, now think about what that's going to do. But first, although I have already alluded to this, potassium here is our neutral ion because it could have come from a strong base, right? Potassium hydroxide, that's how I like to remember that. Your acetate ion could have come from, now this we have done examples on, a weak acid, right? Acetic acid. Very common example of a weak acid. So this could have come from a weak acid, so its ion can act like a non-neutral ion. In this case, this ion can act like a base, the acetate ion. Okay, how exactly? Let's see. And I thought I showed you here, but I'm going to show you right now. Okay, just gonna give myself some room here. All right, so not H. All right, acetate inside water, HOH. Now, this can pull the positive hydrogen. Okay, leaving therefore hydroxide. Right, way back in that slide, where I said negative anions can tend to, they don't always, but they can pull out the positive hydrogen ion or the positive cation, leaving hydroxide. This from water can pull out the positive ion, leaving hydroxide, therefore acting like a base. And this is a good example of this occurring, but it has to meet the requirement that it came from a weak acid. Okay, so in general, basic ions come from anions formed from the dissociation of weak acids, right, such as acetic acid. Okay, and this is a mistake here. Can't seem to click on it, but it should be HCN. Okay. Also, loss of cations in molecules like bicarbonates. So HCO3, right? Bicarbonates that can also therefore act like a base. Okay. Similarly, positive, right? Okay, so it can act like a base as well, pulling out a hydrogen and leaving hydroxide. Okay, so to summarize, in general, ions created by weak acids can create basic solutions. Of course, that's from their conjugate base. And weak bases can create acidic solutions. That's from their conjugate acid. Again, they're conjugates. Neutral ions come from strong acids and bases, and left or right sides of the periodic table. Okay. Summary, just a general summary here of what we just discussed. Okay, important to wrap your head around this. I know it can take a little while. There are a few questions here. Pay attention specifically to question 4. We can take this up later. I hope this helps. Post any questions. Let me know how I can help.